overview of some things that we are covering in class in shorter way. So this book that I'm circulating right now is the when you look by card of Gaussian, one is getting certificate. It makes really hard if you are diving deep into the theory. It is not deep enough in anything, but it's a good survey for you. If you are not strong, like chemistry is not the primary background, you may be surprised by too much of chemistry. But if you are like organic chemist, you need like that's same as other things. We will go deeper into this book in time.
Why is the part?
Because not like I like person, not like I like iPhone, but I like imaginary unit. If you take its square, you get -1. And in the definition of momentum, you have so when you take second derivative, when you take p squared, so you have -1 squared, I squared, h squared, d2 dx squared. So -1 squared gets 1, I squared gets -1, and then you have this h bar squared negative, so negative. And if we are in the atomic units, we can drop h bar.
Don't we end up getting for like kinetic part, the momentum divided by the mass?
Yes. Yes. Good.
So if we have one electron, the question 1, why does the kinetic part show up for the electron?
It does show up.
Does it show up? That's one.
Yes, because electron can move. Yeah, so there are two. You're asking a question about the homework. We all have this thing. The equation on the page 1. Wait.
Sorry, wrong.
No problem. So page 148.
Yes.
-1/2 gradient squared.
Yeah.
Right. So 1/2 comes from definition of kinetic energy through momentum. We can get rid of a mass, and gradient squared is second derivative. So the main question is number of terms. So you have 1 kinetic for electron, 2 kinetic for ions, 2 potentials for electron to nuclear, and 1 potential for ion to ion. Right?
Yeah.
That's it. And there is no electron to electron repulsion. Right?
So I was just thinking that he feels just one electron, there will be like no, I mean, due to like there's no repulsion, and with just one electron, you wouldn't have like the kinetic for the electron part.
Yes,
That's-
kinetic for electron part, but then this electron is getting attracted to ions.
Okay. So,
Oh, so who we are and what are we doing?
Did we already turn in homework?
Some of us do. Thank you. So we are trying to fill this table with recordings, right? It's a goal of the course, and we are in the molecular modeling part chapter, where most interesting things are on Wednesday nights. I'm trying to design homework for the next weekend, but trying to make it the same level of complication or easier than it was, so that you do not worry. It's hopefully a really easy thing, but I have shared the notes, and you can see approximate way of what it will be about. So here are your votes for your practicing of democracy. So in a week and 2 days there will be presentations. So when we will be here tomorrow and next Wednesday, hopefully things will work on recording, but who knows. So please, when you do something, do screenshots and save them into PowerPoints, especially if we are doing something related to your favorite area of presentation. So on the lectures we are doing with green stuff. No, green stuff on the practical assignments, and on the lectures pink, right? And your homework has a couple of terms less because there is no second lecture. But we are building. It's a review, nothing new. So lean back, fall asleep. I will tell you when to wake up.
Did we go over the extra credit?
We haven't even talked about the assignment.
Oh, okay.
Huh?
So we haven't really talked about the assignment.
We just had a debate on the extra credit, so we're trying to figure out
What do we want to debate?
a debate. Like what we understood. Like I feel like most of us understood the 3 parts for the assignment, the 3 charges, but some of us were arguing the basics on the extra credit, like looking at the lithium hydride. So I was just curious.
So just lithium, proton, charge 3, and then 1 more electron. So you just draw a few more arrows.
Okay, so there's a total of.
Two nuclei and 3 electrons.
Okay, you're
Right.
almost there.
Am I wrong? I can be wrong.
4
Four electrons, yes.
Well, yeah, we were debating too. There's a lot of debate. The valence electrons, were we just looking at them, or were we looking at all total that lithium has? We didn't know.
Oh. It's the goal of this meeting, of this homework, was to, on one hand, show how everything is simple, on the other, to scare you of how many terms and give motivation for letting computers do jobs instead of us.
It worked.
Right.
Okay.
So,
Because if you're gonna have 7 terms, you're gonna have 7. Well, you're gonna have the 7 points in the Cartesian, right? And then you're gonna have those points within those points interacting. So that's gonna be a huge mess.
even for such a simple molecule, if one wants to do pure quantum description, it's quite heavy. There are actual articles, research articles, when people do it, but it's not of practical use because by today's computational power, you can scale it up for larger things.
So,
Yes?
always the kinetic energy of nucleus is considered as 0.
No. Well, when we write equations, we explicitly, before we do approximations, kinetic condition of new class is not zero. Because everything in the real life exists at root temperature. There is a motion of gas.
But it is moves.
Over time, unless you are at absolute zero, you will continue, even though there are quantum effects responding to like zero or line or some more divergence. So the terms of the Hamiltonian should be there generally.
Constant.
Well, this is not literally key for the homework. It is like chapter of one of the simple texts, and the goal is to convert molecular Schrödinger equation and molecular Hamiltonian into something that we can solve. So basically, it is what we do here in class. So we declare and slowly derive Born-Oppenheimer approximation. In this printout, they try to explain it in words. We are trying to go deeper and explain it in equations. I'll bring a couple of other printouts with more deeper things. Make sense? So once again, where we are, what are we doing? So we realize that for even small amount of nucleus and electrons, there is a huge amount of terms into Hamiltonian that we need to plug into Schrödinger equation, and you immediately see and feel that it is too much. So even before delegating right to solve equations to a computer, we may want to simplify a task. You may have seen it before. Simplify a task. So reduce amount of degrees of freedom. Simplify Hamiltonian onto something shorter that we can solve, right? So we are practicing divide and conquer approach, and our first goal is to treat separately electrons and nuclei, right? So what we did, we have regrouped terms. Everything that more or less related to electron is our electronic Hamiltonian, and everything that deals with nuclear degrees of freedom we keep yet in the molecular Hamiltonian. So keep sleeping, do not focus. I'm repeating what we did before. So if we take three terms in the Hamiltonian that deal with electronic degrees of freedom, or electronic degrees of freedom are independent variables and positions of nuclei are parameters, we can assume that this Schrödinger equation for electrons has been solved, right? If it has been solved, then we do have the set of eigenfunctions and eigenenergies, which both depend parametrically on positions of ions. And then our approach was to construct superposition of all available electronic wave functions with some temporarily unknown coefficients and plug in this superposition into complete molecular Schrödinger equation and see what happens, right? More or less. So we were believing that we know from some sources the electronic wave functions, and the expansion coefficients are at the same time unknown nuclear wave functions. So we did plug this. I think this slide induced most of the questions and discussion last time. So we plugged in the superposition this summation chi phi into molecular Schrödinger equation, where first and second terms relate to nuclear degrees of freedom. The third term relates to everything about electron degrees of freedom. And by the way, our phi functions are eigenfunctions of this operator. And on the after the equation sign, we do have unknown eigenenergy and then our expansion. So what did we do next? Then we decided that we wanted to get rid of the electronic wave functions. And we practiced the, which property? Yes, first normality. So we multiplied everything by this convolution with electronic wave function with another index and integrated. So when we practiced it for lower 3 terms, everything worked well. So we practiced ortho normality, got rid of electronic wave function, and later on we practiced snake eating a rabbit, summation of delta, Kronecker delta. But the first term induced some special attention, because there is operator of kinetic energy of nucleus, but here which is differential operator over positions of nucleus, and here the nuclear wave function explicitly depend on positions of nucleus, and electronic wave functions parametrically depend on the nuclear positions. So by practicing this convolution that should give us Kronecker delta that later can disappear after summation, this trick didn't work for this term, because we applied derivative over nuclear position to both of these product functions. And upon we complete the review, we'll go a little deeper into these terms. None of the practical research, none of the projects will be that we do in class will be related to this. But upon we complete today, maybe next Thursday lecture, we will say goodbye to this part of the equation. But it is an important trampoline for more advanced research that you may decide to dive in at the last meetings of the class or after the class if you want to do something. So we'll go over some definitions used in the community for this quantum effects from nuclear kinetic energy. So it is another slide that we discussed a lot, right? So it was what we did there. So kinetic energy is derivative. Here is the minus sign because of the imaginary, and we applied to the product of chi nuclear wave functions and phi electronic wave function, and so it is application of the derivative twice to the product. So we use derivative of a product as a summation, and then apply it once again. And then there, well, now it is blocked here, but you may remember, you may just run your imagination and see that there are 3 terms. One very normal term, when the, here it is not blocked by this little window. So there is the last term, mostly normal, is when derivative or opposition is applied only to chi function, and this is a pure kinetic energy of nucleus. And there are 2 crazy terms. In one, we take second derivative Oh no, this one is normal, and then there are two crazy. One is we take first derivative of nuclear wave function over of electronic wave function over position of nucleus, and second one when we take second derivative of electronic wave function over position of nucleus. So we may want to discuss: is it possible to drop them? In which situations they are big or small? Which of them are bigger? And general idea is that, like, if function changes slowly, not very steep, then in all theories we assume that second derivative is smaller than first. Right? So typically the first term with first derivative is a little bigger than the one with the second. So by the end of today's meeting, we will get an idea where to keep or drop, what they correspond to in real natural processes, and we'll get a little bit more developed nomenclature that is used in the community for these processes. So I'm not going to keep the intrigue. I wouldn't be patient to wait for the if I would sit in an audience. So what these terms correspond to? They would correspond to transitions between potential energy surfaces. So we'll, you may have heard this term before, right? And we will redefine it once again. So there are so-called potential energy surfaces, electronic states, which are redefined at each position of nucleus. And in conventional computational chemistry, included in all software, we are either in ground or in some cases in the excited state. But typically one doesn't consider transitions between potential energy surfaces. But these exotic terms do correspond to such transitions. And we should arrive to these two equations when we finish even further these two equations at the end of today's meeting. I apologize for the equipment that doesn't allow me to write my finger on the screen. The discussion goes much more vivid if it is possible. But I'll try to put something on the board, or maybe next Tuesday I'll try to bring the some handwriting device to add comments. So, no questions about stuff that we did before. So, I'll try to bring maybe some copies, but what I'm going to do is inspired by this book, which is a little too deep in all other aspects, but in Born-Oppenheimer approximation, it is at the right level. And I was personally acquainted with the author because he was in my thesis committee. So we do, if you apply second derivative of nuclear and electronic wave functions, we get 4 terms, right? Again, keep sleeping, keep relaxing. I will give you a wake up when there will be important things. So it is what we already discussed. So if we apply derivative over nuclear positions to this product of nuclear and electronic wave functions, then we are getting 4 terms, 2 of which do coincide. So let me find which coincide. Derivative of chi over r, these cross terms, they do coincide, they differ by order. So the second derivative of nuclear wave function will be pure kinetic energy. This is a small term which often disappears, just is good to neglect, and this should have coefficient 2. This is product of response of electronic wave function to change in the nuclear position, right? Times first derivative over position of nucleus applied to nuclear wave function. So first derivative over position is momentum. So in fact, when you do this, it will generate momentum of your nuclei. So this is response of the nuclear wave function to change in position of ions, and second term is momentum. If nuclei do not move, then there is no momentum. And then this term will automatically drop. Maybe this, I'll try to repeat this idea, but it is something worth of waking up and record or memorizing. So in these exotic terms, originating from kinetic energy of nucleus, there is a product of something, response of nuclear wave function to change position, times momentum. Momentum of nucleus. So if nucleus do not move, then these exotic terms can be dropped. And then we can think, we can move to analysis of situations when it is these terms can be completely removed, or they necessarily need to be taken into account. So depending on temperature, high temperature, high momentum, non-negligible coupling. So if your reactions that you're considering do have small temperature, if you are doing super cool stuff, like helium, even nitrogen, if you dip your molecule there, you sure can neglect this term. If, yes?
Would, I mean, you're saying room temperature is not negligible? Is that too high or is that negligible?
In case temperature is not negligible, if temperature is low or higher, you shouldn't neglect, or it's questionable if one is allowed to neglect transition between potential energy surfaces. So some people explore how the photoexcitation leads to jump of system from one to another potential surfaces. And when you do excite, it typically means that temperature also increases. So if you have combustion, explosions, photoexcitations, this exotic terms need to be taken into account. If it is like ground state, properties of standalone molecules, if there are no reactions, if you do not burn or explode, it's fine to do a lot of characterization by dropping these terms. Yes, it's a natural wish to erase this term if possible. Strong laser reactions, fragmentation, photofragmentation, photopolymerization, plasma. Yes?
Fragmentation, is that related to clusters?
I don't
Fragmentation, when you mean fragmentation, you mean, what do you mean in this case? Like something
we may use different colloquial languages from different areas. When you induce breaking of a molecule on dissociation on several pieces.
Right. Well, clusters are known to do that. They're not like you compare a cluster versus a quantum.
Clusters of what?
But like small molecules. Like you have bulk. So
it's if you launch discussion.
Nanomaterials
of semiconductors, because
semiconductors.
Okay, good. Because especially I know that there is a part of audience from polymers and coatings, and there are areas of research when people apply words of nanoparticles to like coils of polymers that have nothing to do with semiconductors. So you're not talking about them. Okay.
So you have like clusters, quantum dots, and then you have bulk, like in terms of the size of the material. So when you say fragmentation, I recently learned that clusters like when you have very small, like 1 nanometer size clusters of semiconductor material, they tend to fall apart. They tend not to stay close together depending on the size and the shape. Are you referring to that or?
No.
fragmentation?
You're telling, well, we need a professional inorganic chemist to talk about it, but it is like Ostwald ripening. It's the nucleation of particles in colloidal environment. And then they dynamically associate or dissociate. This is like more in vacuum by breaking molecule in pieces by strong laser.
Oh, okay, gotcha, okay.
And I'll try to ask you a question like listing these processes or something that your imagination will prompt you in the next homework, which probably is simple and legible thing to check. So, some of you get bored because we are spinning around this second derivative for too long, right? So, I, again, stands not for person or for imaginary unit. Now it's like number one, first term, kinetic term. Again, let me repeat because I don't know about you, I sometimes forget what I'm talking about. So, we are plugging in the superposition of electronic states into general molecular Schrödinger equation, and then we aligned it into vertically rather than horizontally to shorten it, and we are talking about first term where operator included only nuclear kinetic energy because like 2, 3, and 4 were easy, and we are focusing on 1. And there, after practicing this kinetic energy, which is nothing but derivative, we see 3 types of terms. So first, when nuclear derivative is applied to nuclear part, it's like pure kinetic energy that we always should keep. And then there are mixtures. So this one is response of electronics wave function to change in position times momentum. This is sometimes kept, and this is very exotic. There should be only 1 second derivative that is dropped almost always. So later on, we may want to refer to these effects and to these terms when you will be writing your written reports or when you do like maybe a paragraph of a figure in your thesis or paper in your major research, and you may want to mention approximations, what you are dropping, what you are neglecting. So we are going to tell that we are typically neglecting these two terms, and we need right language so that people who will read your work will accept and do not click like, haha, it's a person from different community. They do not know what they're talking about. So we better use right words and right notations.
We don't have to say why.
Oh, low temperature ground state, therefore we neglect them. But them whom? Crazy terms that originate from kinetic energy of nucleus. It's correct, but a little too long. The right word would be non-elevating complex or transitions between potential energy surfaces. So the only reason to spend another half an hour is to formally get through these notations. Okay, so here is what we are getting from the first term when we plug in the superposition of electronic states into total molecular Schrödinger equation. We are getting pure kinetic energy, and we get 2 exotic terms that we want to drop. These 2 exotic terms, two types of terms, because there are several of those, they will not give delta functions. So by convolution of electronic states A and B, we are not going to get diagonal matrices. By the way, let me slow down and ask if
who is feeling comfortable with bra and cat notations? Very comfortable. 1, 2,
What rotation?
3. Bra and cat. 3. Who is completely discomfortable and never heard about bra and cat notations? 2, 3. Okay, 3 versus 3. So the rest, who has heard but not confident? 11 minus 3 minus 3 and 1 missing. Okay, so let me bring it up real quick. It's just a background from quantum theory, and I'm not going to tell you anything. It will be just notation. So when you do have integral phi star b some argument times phi without star a some argument dr, it is often replaced by notation phi b times phi a. So when you numerically do this operation, it means you take value of this function at point r1, at point r2, point r3, and phi a r1 times phi r1 plus phi.
The product rule.
Yes, yes.
From that.
Phi a 2. So a lot of terms, and we put delta r out of brackets, right? So it looks like scalar product in space of infinite number of dimensions, right? And scalar product is like product of two vectors, vector A and vector B. And products of two vectors looks like two brackets, one from left side, one from the right. Bracket. So left part of the bracket is bra, right part of the bracket is cat. So the reason for this notation is only to avoid sign of integral and dr, right? So we are practicing it here. And between these two things, there could be another operator, still bra and cat notation. So we have these exotic terms between bra and cat, so it's a derivative over nuclear position applied to electronic state. Second derivative. Here is the first derivative over nuclear position applied to electronic state, bra and cat. And then it is multiplied by momentum, which is application of the derivative of over nuclear position to nuclear wave function. So we do have summation over all electronic states, A here, A there, right? Because originally we plugged in superposition. And in all terms except these two exotic ones, the bra and cat generated delta function, and summation makes an appointment with delta function and eats it on the appointment. And then, right? And then instead of series of several terms, there will be only one term, and we roll into simple equation. So these two terms are characterized by the fact that this bra and cat of nuclear differential operators do not give delta function. They give some other function. And you see, there is summation, there is something, and then there is this chi sub A. Why don't we call this something like theta AB? And we also, yeah. So because this term depends on index A and index B. So if it would be an easy story, then this theta AB will be delta AB, will be Kronecker delta, unit matrix that we can discard process as needed. But it is not equal to unity matrix. It has some off-diagonal terms. So this theta AB is called non-adiabatic coupling. It is a measure how happily system may jump from different potential energy surfaces. It measures how efficient this system jumps from state A, electronic state A, to electronic state B. Good? Make sense? And we are developing an idea and verbal formula that at low temperatures there are no transitions between different electronic states, and we can drop this stuff. So we have name for it, non-adiabatic coupling, and we have notation for it, like theta sub AB. I'm missing times when, in addition to writing by finger, you can flip slides by just waving hands. Maybe you can put a sensor, or like Siri, next slide. There is nothing new. It's just handwritten notes that illustrate what is here. So this derivative, if you put like minus I and H bar factors, it will be nuclear momentum. Later, lowercase m was not ideal. It's better to use I capital. That's it. We already get main conclusion. Again, let me repeat. These exotic terms are called non-adiabatic couplings. The notation for them is theta sub AB, and they can be dropped if temperature is low, because their main purpose is transitions between different potential energy surfaces. Oh, it was already here. Bra and cat. I was.
Well, it's a
Russian.
B, no?
B.
I thought it was G.
No, not gra. Bra. Like bracket.
Bracket.
And you know, sometimes you can swap their order and have cat bra. So if we drop a second order term, theta AB is matrix element of the gradient in respect to nuclear position multiplied by momentum. Good. So it's accepted in the community. Some people like to multiply it not by momentum but the change in the nuclear position, which is also acceptable but less common. Okay, so going back to where we started. So originally we had four lines in the equation. First line for nuclear kinetic energy, and then nuclear repulsion, then eigenstates of electronic state, and then bigger eigenstate of the overall molecular system. Now our first term split onto two parts. One is like standard, canonical, pure kinetic energy of nucleus multiplied by delta function, which creates no problem. Then, and the exotic non-adiabatic couplings that is not diagonal, that creates problems. So another side of this problem, I apologize if you already got it all and I'm mumbling too slow, but another side. In case we have high temperature, in case something is burning and exploding, in case there are transitions between different electronic states, in case non-adiabatic coupling is not negligible, we cannot separate electronic and nuclear degrees of freedom, and we cannot do anything. Our task, our equations stay really complicated, many degrees of freedom. So, on one hand, it's really like cool. You do something that is exotic and interesting, and when things, I don't know, some people become chemists because they like burn things or explode things, right? It's really cool. But when you're looking on the convention of completing some calculations, when you need to characterize a material, you do want to separate electronic and nuclear degrees of freedom, and it's your first intention to drop this term. Even if it is not possible, assume for a second that it is possible to drop. Okay? Drop it. And then practice this meeting between delta function and summation that will remove them both and change the index from A to B, from A to B, from A to B. Good? Now we have 4 terms back. We assume that our temperature is low, even if it is not low, because it's so appetizing to have to drop half of degrees of freedom and make problems several orders of magnitude simpler. Even if it's not completely legitimate, we can tell it is our approximation. We first consider it in a simplified way and then take into account another effects. So what do we get if we drop, if you complete this convolution? You get 3 terms: pure kinetic energy, nuclear repulsion, eigenstate of the electronic Schrödinger equation, which parametrically depends on position of ions, act on the unknown nuclear wave function. See, we still have nuclear wave function. We are not too. We did some real breakthrough, but we still have electronic nuclear wave functions. Nuclei are quantized, and then eigenvalue of the molecular Schrödinger equation, which is energy of the whole system, electrons times plus nucleus, multiplied by the same nuclear wave function. So under this transition from overall molecular Schrödinger equation to a pair of equations, one equation for electrons and another for electronic wave function and another for nuclear wave function, is known as Born-Oppenheimer approximation. Or if you are tired to speak many sounds, you can say BO approximation. Now, let's look with more details on this stationary time-independent Schrödinger equation for nuclear wave function. What do we see there? You know from kindergarten that Hamiltonian consists of kinetic and potential energy. Kinetic plus potential equals 2. And here we have 3 terms. No, there should be 2. So we should associate 2 terms into one. So n-coulombic nuclear repulsion plus eigenenergy of electronic state that parametrically depends on the positions can be referred to as potential part of the Hamiltonian for nuclear Schrödinger equation, right? And we can call it, again, if I'm lazy to speak, PES, stands for potential energy surface, right? So potential energy surface is not only nuclear repulsion because of Coulombic repulsion, but it also includes a part that originates from all forms of electronic interactions, right? For example, if I have an ion, another ion, they repel like crazy. But if I put some butter around, well, electrons, on another one, electrons will screen this their hate, and they will repel not as strong. Maybe in some cases they even can start attracting. So electronic clouds may make wonders. Bind ions together, form molecules. So you cannot neglect electronic part of nuclear-nuclear interaction. And for this part, one needs to do quantum calculations for electronic degrees of freedom, on one hand. On another hand, if you have a million molecules, if you are doing polymers with molecular weight 100,000 or whatever, you cannot do quantum calculations, but you may parameterize your force field, your interatomic potential, based on previous solution of electronic problem for smaller molecules. And typically for bigger polymers, one does only the ground state. There is another thing. So from one point of view, what we do has some new things. From another, I would be not surprised if some of you tell that it is really boring, that we are just rolling around the same equation again and again, just analyzing, looking from different angles. Once I've got student feedback after the class, and I was reading what is there. So I was like, I learned nothing new, it was so trivial. But we better talk about trivial things first and then maybe go to something advanced. So, the letter B here. Where it comes from? What does this index mean? It means that this is eigenstate number B of electronic problems, of electronic stationary Schrödinger equation. And Schrödinger equation typically has more than one solution. Therefore, we need index. So if you were relaxing, now it's time to wake up. There is something that we will not neglect. We will use all the time. So the potential energy surface, which means potentials, or you can easily convert it into forces between each pair of nuclei, do depend on electronic state. If system is in ground electronic state, it will be one force. If it is in excited, it will be different force. So interatomic interactions generally depend on state of electronic system. Therefore, so this index tells that there is more than one potential energy surface. As many potential energy surfaces as many electronic states. In real life, in real calculations, everyone does ground state, and depending on the necessity, one can do like a couple of excited states, or maybe like if it goes with spectra, one can do like maybe 100 excited states. But what should we tell to Anas?
This is important.
This eigenstate. This is the eigenstate. The B term is from the eigenstate of electronic part of the Schrödinger equation. So we need to know that. It's a very important term.
Potential energy surface
Fragmentation.
between interaction between nuclei depend on electronic state. So if the system is electronically in ground or electronically excited, ions attract or repel in a very different way. Okay? So this is probably most important part of today's meeting. Ben did experience this in his PCAM project, right? Ben, in green shirt. he's well aware of this important feature. There is no Siri in this computer, so tell Siri next slide. Do I have anything else? The same. Here is, well, I can draw it on the board, but here it is. In ground state, the potential energy surface typically has minimum, right? Which means that due to additional electronic screening, ions in a molecule want to stay nearby at certain distance, which we call bond length, right? But if you are going to potential energy surface with different number, right, different than 1, then the dependence of the nuclear repulsion plus this term, potential surface, on the nuclear coordinate can gain additional features. Simplest one, the equilibrium position may change, which means bond length, equilibrium bond length often depends on electronic state. If you excite it, it like expands or sometimes contracts. The simplest one, if molecule stays intact. Sometimes excited state may develop more than 1 minimum, like photodimerization, photoisomerization. And I didn't put it here, but sometimes nature of interaction may change upon excitation. Like in ground state, it can be attractive, and in excited, it can become repulsive. Like the simplest example, if this year is too late, but next year I may do it as an example. If you take your homework task number 1, potential energy surfaces for H2 plus, and considering this molecular hydrogen, neutral or ionized in ground and excited state. In the excited state, many diatomic molecules dissociate, decompose. So potential, instead of minimum, it's getting the dissociative potential. So if there is no minimum, then whenever you start, there will be force So if there is no minimum at any place, will be force dragging it away from being close to each other, and the molecule will decompose. So if we are looking only on force field molecular dynamics for really big molecules, then we do need to purchase, buy, steal, inherit potentials, potential energy surfaces, primarily for ground state. If we need excited state potentials, we again need them. And if we have a luxury to work with relatively small objects, we just need to recompute potential energy surfaces by rerunning electronic structure at each interatomic distance. Okay? Make sense? So interatomic attraction or repulsion drastically depend on electronic state. Oh, it's departing carcass here. So I did this comment because being myself excited about this material, I'm always forgetting to tell it. So when you were listening to what we were discussing like 5 minutes ago, there could be a deceptive impression that under Born-Oppenheimer approximation, electrons and nuclei do not interact. No. If you got this impression, I did poor job. Electrons and nuclei do interact. Positions of nuclei affect electronic states. Electronic states affect internuclear potential. So there is interaction of nuclear and electronic degrees of freedom. Born-Oppenheimer approximation decouples mathematical representation of electronic and nuclear degrees of freedom, and it explicitly forbids jumps, forbids transition between potential energy surfaces. So it's Born and Oppenheimer kill only part of electron-nuclear interaction. They kill the transitions between potential surfaces, but they do not kill dependence of interatomic forces on in which surface we are, and it doesn't kill the dependence of electronic energies on how far we displace the nucleus, right? Good. Okay, before we depart in peace, there is another little comment. I want, by the way, congratulate you that you have passed most complicated part of the, I don't know how to put it in figures, on the lecture material. You are ramping up. Starting from now, you'll get to simpler and simpler concepts, simpler and simpler equations. We still need to do some work, but it was most complicated. And the most complicated part of the course was not most complicated part thing in the world, right? But things will get simpler. So, you do have Schrödinger equation, which is stationary, which is time independent, for nuclear wave function, right? If you solve it, we get how that nuclei are allowed to stay. There is a better probability to stay at this distance, lower probability at another distance. It is quantized. There could be like harmonics for oscillations. But it is a stationary equation. In real life, when stationary equations, Schrödinger stationary equation, when time-independent Schrödinger equation is needed. When we have some certainty that system is created in one of the eigenstates in the experiment that you described. But if you know that system may be prepared in the superposition of the eigenstates, it will be in non-stationary states. It will expose dynamics. It's on the side of pure quantum theory. On the side of a little more practical, we already know nuclei are moving, right? They're changing in time. Why should we focus on the time-independent Schrödinger equation? There is no one twists our arms to do so. As soon as we have agreed to have kinetic potential energy, we have Hamiltonian that refers only to nuclear degrees of freedom, we can immediately tell, oh, no, it was only the first step, and now we can do full-scale time-dependent Schrödinger equation. It will be not much more expensive, right? You know, for time dependence, you just add derivative over time, right? I even do not do this votes. I'm sure that you have practiced time-dependent Schrödinger equation starting from the kindergarten, and you can reproduce it with closed eyes, right? But just in case, let me write it down on the board. So if you do have Hamiltonian, and you want to say that your wave function does depend not only on position, but also on time, we need to practice time derivative. So check how does it change with time. But the Hamiltonian for time dependent and time independent Schrödinger equations is the same. Okay? So as soon as we agree of which Hamiltonian to use, it's mathematically, especially if we're just writing equations, there is no much difference. Time dependent, time independent, they are naturally interconnected. But from intuition, atoms are moving, changing in time, so we need time dependence. Why don't we take this Hamiltonian and use it for time dependent Schrödinger equation? I see it's not very visible. So if you solve time-dependent Schrödinger equation, what are you going to get? Typical solutions. Like if it is time-independent Schrödinger equation for potentials, interatomic potentials, which often looks like harmonic oscillators, you'll get harmonics like Gaussian, then Gaussian multiplied by linear, it's like camel with 2 humps, then camel with 3 humps, right? But if you explore time dependence for maybe Gaussian that was slightly displaced, what are you going to get? I'm sure that you all know. I know I'm absolutely confident that there is a gentleman who practices it recently and maybe teach all of us. So if in harmonic potential we slightly displace ground state wave function, what will happen to it?
So it will oscillate, like it will oscillate between two different surfaces.
Two different vectors of
In the one.
Yes, in the one. Right? So if we have potential, we select initial state which will be like Gaussian distribution but displaced from equilibrium, and we let it go according to time-dependent Schrödinger equation. This initial state will start move forwards and backwards. If you are looking at probability distribution, if you are looking onto wave function, during the motion, it will change the shape and will explore some fringes. But the envelope function, where these fringes are distributed, it will keep Gaussian shape. So this Gaussian shape, this is interatomic positions. This is simultaneously the potential E plus N, and at the same time it is the psi of R and T. So the envelope function for this solution of time-dependent Schrödinger equation, or square of the absolute value square, shows distribution at which interatomic distances it is more probable to find the system. So there are quantized nuclei. It means that they can simultaneously be on several of interatomic distances with certain probability. And the position where it is more probable to find may change in time. It's a function with fringes. But if you are simple guys, if you are not picky about exotic quantum effects, we can assume that width of this Gaussian, it's called sigma, width is so much smaller than equilibrium interatomic distance that one can approximate this Gaussian as a delta function. Where center of this delta function will move forward and back according to trajectory. Some of you may tell it's evident and not rigorous. Trivial things. Some of you may tell, like, give more explanations. Basically the same. So,
Is one like easier than the other?
oh yes, absolutely. So, the nuclear wave function that we believe in is complicated object. As many independent nuclear positions, as more complicated this multidimensional function. Just by my poor human abilities, I draw it as one-dimensional, but typically it's like number of atoms times 3, multidimensional. And distribution in multidimensional space is really hard. And if it changes in time, it's even harder. But why don't we select average, mean position of interatomic distance, or all interatomic distance, and tell that, okay, they are just classical trajectories. It will be so much cheaper. So instead of this distributed objects, wave functions, we will have just a couple of numbers at each point of time, trajectories. It's a really, really appetizing idea. If you can implement this idea. So how can we do it? Does anyone allow us to do so? And of course, if you want, we will do it even if no one allows, right? Just because it is so appetizing. But is there a person who proved a theorem allowing us to do so?
Hopeful? No.
Maybe 80 years ago. Huh?
Running.
But it's more about periodic potentials. I'm sure that Ben knows the answer.
Why?
Huh?
Why?
You may. So who let me formulate a question. Let me formulate it in such a way that you would be able to find it on Wikipedia. So, is there a theorem that allows transition from quantum theory to classical theory? Is there a way when we can continuously neglect a parameter? Huh? De Broglie, it's like opposite. It tells like any particle is a wave. But if you want to go backwards, from the wave back to the particle. Huh? No, Fourier is just going from Cartesian to momentum, or from time to energy. So,
Einstein.
no,
I'll just throw it.
no.
Is it like decoherence?
Wait. Of course, if you do this transition, you assume that decoherence happened, but it was a person who was a teacher of several fathers of quantum theory, or was a little older than them. He's in this group, but it's not him. Huh? No, a little older, but same range of years. So, if the name starts with E, last name. Second letter is H. Yes. So there is an Ehrenfest theorem telling that if you take a limit when Planck constant goes to 0, and you are setting up equations for expectation value of position, Well, instead of psi, probably we should use.
What's the name of the theorem?
I'll erase everything.
Okay.
And therefore, writing on the screen is a little better. That you never need to erase.
Well,
Unless you do something really wrong. So if you do nuclear wave function solution of time-dependent Schrödinger equation, then you write down expectation value for position. That computed based on Schrödinger equation. In case Planck constant goes to 0, it will generate the same trajectory as one generates from Newton equation of motion. So, if we replace Schrödinger equation for nuclear part time independent to time dependent, we generate time dependent nuclear wave function. And if we assume that quantum effects, if the width of the distribution is negligible, if we believe Ehrenfest, then we can make a trick and tell, like, let's live a simple life. Let's generate average positions of nucleus based on Newton's equation of motion, which is like several exponential number of orders of magnitude simpler than anything quantum. The only stuff that we inherit with from our very advanced consideration is that we take potential energy surfaces that depend on electronic state, and we plug them into Newton's equation of motion. So, due to Ehrenfest, we replace time-dependent Schrödinger equation for nuclear wave function on two classical trajectories computed by Newton's equation of motion. What I'm speaking is slightly diverging what I'm showing. Let's go. Yes. So we formulate potential as Coulomb nuclear repulsion and quantum part, eigenstate of electronic part, like screening and such. And then we convert the time-dependent nuclear equation of motion into time-dependent Schrödinger equation of motion, into Newton equation of motion that generates trajectory with this potential. It has some imprint of quantum properties of electrons. We all are smart. We use quantum nature. But by the cost of calculations, we do classical things that were possible to compute even without computers. And with computers, one can do it for millions of atoms. At least for hundreds, easily, like hyper force field, optimization of force field molecular dynamics. Okay. I told a little bit more than I was planning to. But I think you don't mind.
Question.
Yes.
So I like to think of things in examples. This helps me to visualize how we're doing things. So I come from the side of the quantum side where we are dealing with, small molecules that we're looking at semiconducting material. And now I'm in the polymer world where we're looking at long carbon material. When we learn about these different calculations between quantum and classical mechanics, are is there like a hybrid in the middle? Are we going to be like focusing on one end where we start really small on the atomic level, and then we switch over to the macro size and we start looking at those surfaces? Do we start to see that kind of hybrid middle in the example between our extremes?
Yes,
Okay.
it's more art than science when you go away from extremes, but it's not answer. It's just one of the examples. In order to go this what we call E sub b of R, one needs to solve quantum problems for very small atoms, small molecules of few atoms. Then one can reconstruct potential energy surfaces between pairs of certain atoms and use them as parameters for force field problems that solve for like million of atoms.
So
Stepwise.
Okay. So are we only looking at pairs, or are we looking at maybe chunks? Does the chunks get bigger?
One can use bigger data sets for training of these
Okay.
interatomic forces.
Okay.
It's not the whole story, but I think you partially addresses.
Yes. Yes.
I'll stay here to answer any questions, if there are, or if there are no. But formal meeting is done. Looking forward to see you on Wednesday at 5
In this room.
in this room.
Okay.
Yes.
Tomorrow, or assignment, so you're saying there's 2 nucleoids that assignment. So for the lithium hydroxide, and then you're saying there's 4 electrons. That's what it's diagram system.
So wait.
Should have been 2 and 4. So
Two.
4 electrons and 2 nuclei.
Okay.